Hello everyone, this is Amir. Today I'm going to talk about a project for Renewable Energy course under supervision of Dr. Iqbal. My project is about design and simulate a wind turbine powered electric car charging system for St. John's. Here's outline of my presentation. First of all, I'm going to talk about wind turbines and different wind energy conversion systems, and then touch upon electrical vehicle systems and different arrangement of standard charging systems for a charging station. And then I will provide my purpose scheme of a system and the result of system sizing by using software called Hummer. After sizing the system and analysis, I will provide my output result of simulation on Simulink. At the end, I will talk about vital system protection and system control. Basically, there are two different type of structure of wind turbine: horizontal axis wind turbine and vertical axis wind turbine. Horizontal axis wind turbine are used widely because they tap more wind energy, but just from one direction, while vertical axis wind turbine can tap energy from any direction. Here is some advantages and disadvantages of wind turbine design. Uh, Generally speaking, horizontal axis wind turbine are used for high-grade systems because they have full range from watt to megawatt power. And also we have a more electrical and mechanical control like yaw control and pitch control on these kind of turbines. But on the other side, we use vertical axis wind turbine for standalone systems, even just for one household or pico systems, because they are easy to install and take less place to install, and they have also a simple design because they have no yaw or pitch control. Also, because their gearbox generator are installed on the ground, they are easy to install and maintenance. These days, mostly we use three different energy conversion systems, which are based on a permanent magnet synchronous generator, a squirrel cage induction generator, or double fed induction generator. It is common that for a standalone system we use a permanent magnet synchronous generator, and for grid-tied system we use DFIG. But like any other system, they have their own advantages and disadvantages. But most significant advantage of permanent magnet synchronous generator is that they can operate at a full range of wind speed, and they are brushless, so they need less maintenance. But we use the DFIG for a grid tie system because we have a full control on active and reactive power independently. There are three typical electrical vehicles: battery electrical vehicle, hybrid electrical vehicle, and plug-in hybrid electrical vehicle. Battery electrical vehicles are fully electrical vehicles which their energy provided only by their rechargeable batteries. It means once the battery is fully charged, it can drive until it uses all the battery stored energy. Hybrid electrical vehicles use both internal combustion engine and one or two electrical machine, which depends on its configurations. These vehicles don't need plug-in systems because it can recharge their own batteries using converters which convert the mechanical energy to electrical energy and vice versa. Plug-in hybrid electrical vehicles first start at fully electrical mode, and all its energy comes from the batteries. When the batteries energy reach a specific low level, the internal combustion engine start until the end of the trip. The batteries can recharge through both regenerative braking and plugging. According to Society of Automotive Engineers, we have two standard systems, AC charging system and DC charging system, which each systems divided to three levels, which each levels have a different voltage and current and should provide a specific power to be proper for a charging station. So far, we will look at basic concept of a charging station that we was supposed to first have a look at those. From now on, I'm going to talk about my purpose scheme for a charging system. This charging system consists of wind turbine and its tower, converter, battery, which are chosen for providing power to charge an EV like Kia ESO. First, I've chose the wind turbine, which is the most important part of the system because all energy is provided by the wind turbine. The Bergy XL10 is selected because we need a wind turbine with at least 7 kilowatts for its nominal output power to minimize the battery bank. The Bergy company also is one of the professional companies, and this turbine is one of the few small wind turbine which has SWCC certification. Generator is the heart of the system which not only converts AC to DC at both directions but also control the battery's state of charge and adjust control voltage and frequency. For this project, a hybrid inverter named Schneider XW Pro 8.5 kW hybrid inverter is chosen. This inverter is used to convert input variable 200 to 240 volt AC to 48 volt DC for charging the batteries. Also, once the system needs energy from the batteries, it converts input for the 8 volt DC to 230 volt AC. In addition, it fixes the output voltage with pure sinusoidal waveform, and also it controls the battery charging process. To build a 48 volt DC backup energy system, a series of 4 number of 12 volt battery is needed. So Trojan SAGM 12 to 205 battery could be a good choice. This battery has reasonable capacity and a high lifespan. The aim of this project is that to design a charging station for Kia e-Soul 2019. This is an EV car which is equipped with two type of battery capacity. This car supports both AC level 2 and fast DC charging level 3 systems. As you can see in this picture, this EV equipped with a 7.5 kilowatt charger, and it takes about 6 hours to become fully charged. So the charging station is supposed to provide at least 7 kilowatt for 6 hours. I've used Homer Pro for sizing the system. Homer is a software that provides this ability to design hybrid systems and like data, actually real data from a NASA website for wind or solar resources. For my purpose, I define a project with a location near the Avalon Mall. And the scenario is that an Avalon Mall employee is going to charge its electrical vehicle car for 6 hours from 9 a.m. to around 2 p.m. So the charging station is supposed to handle this demand every day. As mentioned previously, the charging station should provide 7 to kilowatt hours to charging the Kia e-Soul. And then I chose the Bergy Excel 10, and I like the data as which is compatible with my scenario, and the converter and the battery, which all of them have the exact property as I mentioned before. This slide presents the output simulation of Homer, and Homer proposed this optimum system, which consists of one Bergy XL10 turbine, 10 strings Trojan batteries, and one converter that has at least 7.8 kilowatt capacity. As you can see in this slide, the total cost of this project would be around $145,000. So far, we did a static analysis and found that the size and needed capacity of our system components. For dynamic analysis, we use Simulink. In this slide, you can see the Simulink model of the charging station system. Here is our wind generation model, which its input is wind speed. Wind speed could be constant or could be variable, and the output is the three-phase voltage. In the next slide, I will go into more detail about this wind generation model. All these parts, actually AC DC AC converter, filter, the bidirectional DC to DC inverter, and the control part represent our Schneider XW hybrid inverter. This battery represents our battery backup, and this load represents our EV car, which consumes about 7.2 kilowatts. This is the subsystem of wind generation model. As you can see, here is the model of a wind turbine, and this is the model of a drivetrain, actually our gearbox, and this is the model of a permanent magnet synchronous generator. This slide shows the battery charging control and protection. Actually, this part is a bidirectional DC to DC converter that is controlled with a voltage controller to provide a constant DC voltage to charging the battery. This part protects the battery from overcharge or over discharge. Actually, this system measure the state of charge the battery and keep the battery state of charge between 20 and 80%. This is the measure output voltage and current of the load and the voltage of DC bus. As you can see, our system could provide pure voltage for the load and constant voltage for the DC bus to charge the battery. In this slide, I'm going to talk about vital system protection. In order to have a long-lasting system with proper operation, we need system protection. The system protection could consist of AC and DC fuse, circuit breaker, grounding system, and surge and lightning arrestor. AC and DC fuse is a safety device that is installed in series to protect the overflow of the current. Circuit breaker is also a safety device that automatically switches off to protect an electrical circuit from damage caused by exit current from an overload or short circuit. It mainly works with electromagnetic principles. All the standard systems are supposed to provide a grounded system to protect both humans and the system. Surge and lightning arrestor is used to capture the lightning to protect the system from a surge voltage. This slide shows the scheme of protection system, which consists of lightning and surge arrestor, circuit breakers, and the grounding system. Thank you for your listening. If you have any question, please don't hesitate to contact me through this email. Thank you so much.